Oscillator, electronic oscillator, is a modified feedback amplifier with unity loop gain. As in the structure of feedback amplifier, in electronic oscillator structure also, one can find a feedback network or beta network and a amplifier. The beta network usually is a passive network. It is an RC ladder network in case of RC phase shift oscillators. It is an LC network in case of resonant circuit oscillators. It is a Wien bridge in case of Wien bridge oscillator, and it is crystal, quartz crystal in case of crystal oscillators. Colpitts oscillator, Hartley oscillator, they belong to the category of resonant circuit oscillators. In case of Colpitts oscillator, two capacitors and one inductor form the beta circuit. In case of Hartley oscillator, two inductors and one capacitor forms the beta circuit. As already mentioned, in case of Wien bridge oscillator, the Wien bridge, it is the beta circuit. In all these cases, one can notice beta is a passive circuit. When it comes to basic amplifier part of oscillator, it may be a BJT amplifier. In such case, it is called BJT oscillator. If it is a FET amplifier, then it is called FET oscillator. Or it may be an op amp too. Different combinations are possible, hence different types of oscillators. Of course, in all these oscillators, whatever may be the type of amplifier used, whatever may be the type of beta network used, loop gain unity condition or Barkhasen criteria, it is implemented. Then only it works as an oscillator. Before going further, it is required to be mentioned here that RC phase shift oscillators are audio frequency oscillators, whereas resonant frequency oscillators, Wien bridge oscillators, crystal oscillators, they all belong to HF, high frequency oscillators. Electronic circuits oscillators part 2, series on semiconductor devices and circuits, lecture number 10.12. Oscillators are single loop feedback amplifier circuits obeying unity loop gain condition or Barkhasen criteria. Single loop feedback amplifier circuits consists of a basic amplifier and a feedback circuit or beta circuit. If the beta circuit or feedback circuit happens to be an LC resonant circuit, then such oscillators are called resonant oscillators. Resonant oscillators are well known for their high frequency operation. Colpitts oscillator belongs to this category. Hartley oscillator also belongs to this category. Sometimes a bridge circuit is used as beta network. Wien bridge is used most widely. In such case, The resulting oscillator circuit is called Wien bridge oscillator. This bridge oscillator is well known for giving pure sine wave. In the present session, our attention is on understanding the behavior and structure of resonant oscillators and bridge oscillators. Now, let us move to begin the course session. A few points regarding resonant circuit oscillators. These oscillators employ a tuned circuit consisting of parallel combination of an inductor and capacitor. They are well known for their high frequency operation. Here is shown both FET and BJT versions of these oscillators. In A is shown FET version, in B is shown BJT version. RG, CG, they are meant for biasing. R2, C double prime, meant for biasing. R1, 2. RE, C prime. RE is for the stability of the amplifier. C prime is bypass capacitance. One can see here a parallel LC circuit. Parallel LC circuit. One can also notice the coupling that exists to the input side through an inductor, another inductor. Here is shown basic configuration that is followed in the design of resonant oscillators. This is basic amplifier. Here amplifier is indicated by an operational amplifier. This is feedback network. Three impedances are there: Z1, Z2, Z3. Here also Z1, Z2. Of course, in B it is equivalent circuit. B is shown equivalent circuit of the oscillator circuit that is there in A. Notice the design of oscillator circuits. It is based on a condition, that is loop gain angle is equal to 2 pi. Out of this 2 pi, 1 pi is provided by the basic amplifier, another pi 180 degrees is provided by the feedback circuit. That's why notice inverting terminal is being used to connect the output of the feedback network to the amplifier. Analysis gives us the gain without feedback. A is equal to minus AV ZL by ZL plus R0. Loop gain can be found to be, loop gain is minus A beta. A is just found, minus A beta can be found equal to minus AV Z1 Z2 by R0, Z1 plus Z2 plus Z3 plus Z2 Z1 plus Z3. If the impedances are pure reactances, then minus A beta becomes AV X1 X2 by J R0 X1 plus X2 plus X3 minus X2 X1 plus X3. How this relation has come from the earlier relation when we substitute Jx1 for Z1, Jx2 for Z2, Jx3 for Z3, we get this relation. When resistance is 0, it means impedances are pure reactances. Then Z1 becomes Jx1, Z2 becomes Jx2, Z3 becomes Jx3. It results in this relation. For the loop gain to be real, 0 phase shift, x1 plus x2 plus x3 has to be 0. And also minus a beta is equal to av x1 x2 by minus x2 into x1 plus x3 equal to minus av x1 by x1 plus x3 equal to av x1 by x2. Since minus a beta must be positive and at least unity in magnitude, x1 and x2 must have the same sign as ab is required to be positive. It means they must be either both inductive or both capacitive of same kind of reactance. As x3 is equal to minus of x1 plus x2, it must be inductive. If x1, x2 are capacitive or vice versa. So far we considered a general discussion regarding resonant oscillators. Now let us come to specific resonant oscillators. Colpitts and Hartley oscillators fall in the category of resonant circuit oscillators. The architectures of these two oscillators consists of an LC-tuned circuits employing negative feedback. It is ensured that at a particular angular frequency, loop gain of the system satisfies Barkhausen criteria. Colpitts oscillator was conceived by Edwin Henry Colpitts. Well known for his invention of Colpitts oscillator, he was able to improve an inductive coupling oscillator invented by his colleague Ralph Hartley in 1915. He was Bell Labs vice president before retirement. Hartley oscillator was invented by Ralph Winton Lyon Hartley, who was an US researcher. He also invented Hartley transform and contributed to the foundations of information theory. His legacy includes the naming of the Hartley unit of information equal to 1 decimal digit after him. Colpitts and Hartley oscillators are dual to each other. Any one can be obtained from the other just by replacing inductors with capacitors and capacitors with inductors. In Colpitts oscillator, there exist two capacitors and one inductor. In a Hartley oscillator, there exist two inductors and one capacitor. The general form of oscillator circuit consists of an active device, a BJT or FET or op-amp, and a resonant feedback circuit in voltage series feedback configuration. In the basic configuration, x1 and x2 are capacitors and x3 is inductor for Colpitts oscillator as already mentioned. x1 and x2 are inductors and x3 is capacitor in case of Hartley oscillator. Before going further, don't forget to remember that it is voltage series feedback that is implemented in Hartley or Colpitts. Circuits are shown here, BJT versions. In A is shown Colpitts oscillator, two capacitors, one inductor. B is shown Hartley oscillator, two inductors, one capacitor. This is amplifier, BJT amplifier. This is BJT amplifier. R1, R2, C, RE, these are all biasing arrangements. Now we move to another type of oscillator. It is Wien bridge oscillator. In these oscillators, Wien bridge is used as beta network or feedback network. That's why these are called Wien bridge oscillators. These are well known for their ability of supplying pure sine wave. Now a few points regarding these oscillators. A Wien bridge oscillator is a sine wave oscillator capable of generating a large range of frequencies. It was invented by William Hewlett, co-founder of Hewlett-Packard. The modern circuit is derived from his 1939 master's degree thesis. This oscillator is based on a bridge circuit originally developed by Max Wien, German physicist, in 1891. The bridge comprises 4 resistors and 2 capacitors. Hewlett was able to figure out how to make the oscillator with a stable output amplitude and low distortion. The key to this oscillator's low distortion oscillation is an amplitude stabilization method that does not use clipping. Hewlett, along with David Packard, founded Hewlett-Packard, whose first product was the HP200A, a precision Wien bridge oscillator. The circuit of this oscillator typically consists of an active element, maybe op-amp, and a Wien bridge as feedback network. The operational amplifier is used in non-inverting configuration. Wien bridge oscillator circuit. This is Wien beta network. This is basic amplifier. Output of the amplifier is given to Wien bridge. Output of the amplifier is connected to the input terminals. Notice the Wien bridge. There are 4 arms. 2 arms consist of 2 resistors, each a single resistor R1, R2. In the remaining 2 arms, each arm consists of, there are 2 elements, 1 R, 1 C, 1 resistor, 1 capacitor. In one arm they are in series, in another arm they are parallel. The loop gain is minus A beta equal to AV into VI by V0 prime equal to AB, V2 minus V1 by V0 prime equal to AB into Z2 over Z1 plus Z2 minus R2 over R1 plus R2. Frequency of operation of this oscillator is precisely null frequency of the bridge, balanced bridge, which is of course equal to 1 over 2 pi RC. Null frequency of the balanced bridge coincides. It is same as frequency of operation of the oscillator. To ensure magnitude of the loop gain is equal to unity, the resistors ratio should be equal to 2. That is R1 equal to 2R2, but in practice R1 is slightly more than 2R2. This relation has to be maintained in order magnitude of loop gain is slightly more than 1. For unity, R1 requires to be equal to 2R2, but now we know well that magnitude is maintained at a value slightly more than 1. To maintain that, we have to see that R1 is more than 2R2. Tuning mechanism. Provision of facility to vary frequency is highly desirable in oscillator circuits. It makes the oscillator useful in more applications. It's also useful in frequency alignment of oscillator after including in the circuit. In case of Wien bridge oscillators, it is affected by 2 different methods. Continuous variation of frequency is accomplished by varying simultaneously the 2 capacitors. Ganged variable air capacitors are used. For this purpose, changes in frequency range are accomplished by switching in different values for the 2 identical resistors R. Amplitude stabilization. Some modifications to the circuit given are required to stabilize the amplitude of the oscillations against variations due to fluctuations in the behavior of aging transistors, components, etc. They are replacing the transistor or two by a transistor which has a positive thermal quotient, or using a thermistor in place of R1 which has a negative temperature quotient. With this we come to end of this session. Before closing down, let us recollect important aspects that are discussed in the session. Basically, this session is dedicated for introducing resonant circuit oscillators and Wien bridge oscillators, their importance, their structure, their behavior, their properties, all are discussed. Hope you have a useful session. We meet again in another session soon with a new topic.